Okay, so let's finish this bad boy up. So far in this lecture, I've reminded you that what we've been talking about, these threats to internal validity, only apply to experimental designs, which makes sense. Why would you care about ways to avoid things that get in the way between what you know about the relationship between the independent variable and the dependent variable if you're not manipulating any variables, right? So we're only working with experimental designs. We've also talked about some things that do get in the way. We've got the subject and experimenter effects, which can get in the way of internal validity, which can be threats to internal validity in almost any study, and then the longer list of 9 different conditions put forth by Cook and Campbell that can get in the way of longitudinal studies or studies over time. So now we're going to talk about what we can do to control those confounding variables to reduce threats to internal validity. So we say that we are controlling variance because we're identifying what types of things that make the dependent variable vary. So the overview of ways to control variance, one very easy way is to treat groups exactly the same. And I know one of your GAs, Isaac, is in the cognitive psychology lab. And a lot of his experiments or experiments that his lab does are based upon they're computerized. So people will sign up for the experiments, they'll go in and they'll do their experiments on the computer. And one of the reasons that experiments do that, especially those testing cognitive phenomena, it's a little more difficult with social phenomena, but it can be done. But the cognitive phenomena, it's you computerize the whole procedure, you're making sure that you're treating the groups exactly the same. The other thing you can do is to maximize your independent variable or to make sure that your independent variable works. And one way to do this is called a manipulation check. And the best example I can give from this is mine. When I was deciding what to do my PhD dissertation on, one of the things I thought about was stress. I was really interested in the relationship between psychological stress and physiological symptoms in the body. So, a lot of studies I read were about researchers that stressed people out. They do this in all kinds of ways. There are even video games that are supposedly designed to stress people out, to get their heart rate up and their blood pressure going. They'll show them autopsy slides, which I think are awful. They will make them do public speaking, they'll make them do public arithmetic, all types of things to stress people out so they can explore how to unstress people or different aspects of performance under stress. But almost all of these studies, when I first started reading them, they would also ask people, how stressed out are you feeling? So they'd get them stressed out, then they'd ask them whether they were stressed out. They'd either do it right after they stressed them out or at the end of the study, say, remember after you looked at the slides, how stressed out were you? And I thought, well, why did they do that? Because didn't they just get them stressed and they're asking them if they're stressed? And then I realized there's big individual differences in what stresses people out. And so, just to make sure that their people were stressed out, because their whole experiment depended on that fact, they would ask people, are you stressed? And for some people who possibly looked at autopsy slides all day or weren't really into the video game, they could eliminate their data from the study if they weren't really stressed. And making sure that they were stressed is called a manipulation check. And that's maximizing their independent variable. That's making sure that researchers can only work with data from people who the independent variable really made a difference for. So that's one way to control variance. You only keep people in your study who were really affected by the independent variable. Another thing you can do is randomize variance across groups, and we're going to talk about that in a slide or two. And basically, what that means is that you're capitalizing on the laws of chance to make sure that, just like sampling, that you get groups that are roughly equal. And then the very last thing is statistical analysis. Statistical analysis has some steps built into it that help control the part of variance that at least is due to chance. So those are general ways that you can control variance. If we want to get a little more specific, we can talk about things you can do to help combat subject and experimenter effects. These, all told, are called blind procedures. So there's a couple of different blind procedures. The first one is a single blind, and that's when the person testing participants in a study is kept unaware of the hypothesis. For example, I gave an example. How many times can I say example in that sentence? For example, I gave an example a few examples ago about a potential study where the experimenter was weighing people and they just gave the scale, not on purpose, just a little bit of nudge when they knew that the people had gotten the drug treatment because they really wanted that drug to work subconsciously. So, one way to combat that or to eliminate that source of bias is to have the people testing participants in the study, in this example, would be the person weighing the study, doesn't know what group they're in. So, how can they fudge on the people that are getting the drug if they don't know whether the people got the drug or not, or whether they were in the control group? And then double blind procedures are when nobody knows what condition the participants are in. And that helps combat the placebo effect. So often, let's go back to the drug and dieting study. In that particular example, the experiment might have two groups: the treatment group that would actually get the medication for weight loss, and the control group that didn't get anything. But just to make sure that that placebo effect didn't somehow influence the participants themselves, they give the participants who are in the control group a pill as well. And that would be a placebo. Sometimes it's a sugar pill, sometimes it's just some inert chemical formula, gelatin or something like that helps bind pills together. So it still looks and tastes like a pill. But those participants don't even know what group they're in. So their expectations wouldn't affect them because they would all think they were getting some sort of treatment. So those are ways to combat or ways to eliminate threats to internal validity for subjects and experimenters. Another way to reduce those are automation, and that is very similar, just a little more general than the computer example I gave a few minutes ago. Automate everything. And it doesn't have to be on a computer. I know that you have all taken some sort of standardized testing. And you know how when you're taking a standardized test when you were in elementary school, or I think even high school, they still give them. They want to measure students' learnings to figure out how much money the school gets. The teachers always read a script. So everybody starts at the exact same time and the teachers read a script. That's another form of automation. They want to make sure that all of the student groups are set as equal, and they're not given some sort of advantage or disadvantage by something that the teacher or test administrator says. That's automation. Another way is using objective measurements. And they use, and we really, that's what the whole reliability and validity as far as tests go belong to, is to make sure that the measures are psychometrically sound. Anybody giving those tests would get the same results. They're not influenced by a lot of administrator bias. So it's not a lot of judgment, it's an objective measure. It's a measure that involves some sort of measurement or some sort of very, very well documented coding rules so that anybody coding that behavior would get the same results, or coding that measure would get the same results. Related to that are multiple observers. So inter-rater reliability, if everyone can agree and have a specified coding scheme that they all agree upon, it's more likely that the measurement will be stable and related to the person's characteristic and not something else on behalf of the people who are doing the measurement. And then finally, using deception. And that does not mean outright lying. We know that that's unethical. But sometimes using deception might include use of a placebo, or not telling people in the study exactly what the hypotheses are until it's over. Now, ethically, if we use deception, afterward we have to do to everyone involved what's called debriefing. And that's when you get them together and you say, I'm sorry, I had to lie to you. This is why we lied to you. This is the true art of the study. So using deception involved with that deception, even though it really might help eliminate threats to internal validity, because if people don't know what the study's about, they won't even unconsciously influence. We still have the ethical right or the ethical responsibility to debrief people after we use deception. And as I also mentioned briefly, assignment makes a difference. So by assignment, I mean assigning participants to conditions or groups. And the way we do this is absolutely critical to internal validity. And so in order to minimize bias due to assignment, we want to make sure that the groups are as equal as we can make them before. We use pretty much the same types of logic that we use in sampling, and we want things to either be as random as possible to make sure that we don't have any bias, that everything is due to chance. We don't have any assignment bias, that everything is due to chance, or that we get those groups as equal as possible by using matching procedures similar to those we talked about in the last lecture. So finally, we've talked about some ways that we can eliminate threats to internal validity. And when you talk about things you did to eliminate threats to internal validity in your studies, that typically goes in the design section and the method section. So we are finished talking about threats to internal validity, and these last couple of slides I'm going to prep you for with some notation that'll make our next lecture easier for you to take notes and easier for you to understand what's going on. I'm going to talk about design notation. But I want to warn you now, and this lecture is when I always get a little internal giggle when I'm doing it in person, because people's on their faces are kind of like, huh? This seems, the first time you hear it, I guarantee you it's almost not going to make any sense. It's a lot of rules, and all I'm going to do today is tell you the rules. But once you see them in context, they will it'll snap to meaning. It'll make a lot of sense to you. So what I'm doing now is just a little bit of prep for you. Just sit back, relax, absorb it. After you've seen the examples I'm going to give you with the next lecture, everything will get really easy. So this is experimental design notation. Every time you see an X, it means a treatment. It means a manipulated variable. And sometimes you will see little subscript numbers below or next to the X's to show you what treatment it represents, because sometimes in studies we'll have more than one treatment. Every time you see an O, it's an observation, or another way to think of it would be a measurement of something, usually the independent variable. So when you see an O, it's a measurement or observation of the participants. An R equals random assignment. So when you see an R, it means that those groups were randomly assigned. And we've already talked, when we talked about sampling, and then just a couple of slides ago, how important it can be to randomly assign participants to groups. Another critical thing to know is when X's and O's appear on the same line, that means that they apply to the same subjects. And then sort of duplicating the R's, when you see dashed lines between groups, indicate that there was no random assignment of groups. And these rules in this design were, again, from our friend Campbell. Campbell's the same guy as Campbell and Cook. But for these rules, he got together with another friend named Stanley. So these rules are from Campbell and Stanley, and they're often referred to as Campbell and Stanley's experimental notation. So let me give you a couple of examples just to kind of prep you for what you're going to see later. But these, especially if you go to grad school, this design can be so useful because it's a shorthand to show what's going on in a research study that can avoid a lot of words and make understanding what's going on much, much easier. So just a couple examples now. This first one is a pretest post-test design, and there's no control group. Well, how do we know it's a pretest and post-test design? Well, we know that the O's mean observation. So here, this 0, 1, I'm not getting the light there. Let's see. I'm trying to give you some little light, but I guess it's not working. This 0, 1 right here, there we go, is our pretest. And test number 1, we've got a treatment here. That's our intervention or manipulation. And then that's our post-test. So it's a pretest, intervention, post-test design. Pretest, post-test design. How do we know there's no control group? Where there's only one group because there's only one line. Darn it. There's only one group because there's only one line. So that's how we know that there's no control group. Okay, now the second one down below here, we know a little more. The very first thing we know is that there's two groups. Why? Because there's two rows. Two rows, row 1, row 2. Second thing we know is these groups were randomly assigned, which could be helpful to know if we want to critique the study or we're thinking about how those participants got in those groups. We also know, just like the example above, that it's a pretest and post-test. We've got our pretest here. Each group got the pretest. And then we've got our post-test here. Each group got the post-test. And we know it's a control group because only one group got the treatment. This group didn't get any treatment. So we've got a manipulation group and a control group. So keep that in mind. Some basics here just from these simple examples. The number of rows are the number of groups. And O's mean observations or tests. 2 O's is pretest, post-test, and X is manipulations. So next lecture, we'll go into some more advanced designs, and we will use, and you'll be glad you know these. But for now, just relax and think about the internal and external validity, and I will see you next lecture. Goodbye.